All right. So today, what I will talk about is ideas of competition in networks. We saw already a bit of that talking about networks, but I will take that much deeper today and next week. So this week and next week will be very much focused on this idea of competition, what that is in networks. There are various concepts in market theory, in economics of competition, and there are equivalent notions in networks. And so I look at networks from a very economic point of view. I'm not looking at networks from a social point of view. I want to emphasize that again. So that is what I want to emphasize here. So I will go through a number of concepts that express this idea of competition, and more precisely, anti-competition. The equivalent of monopoly and oligopoly, control, in other words, power. And this has everything to do with this connectivity that we introduced before. Who controls that connectivity? That is the question. If there's very little control of connectivity, then the network is competitive. If there is control, it is exactly the opposite of competitive. It is controlled, so to say. And this is exactly what modern corporations, in particular platforms, try to achieve, right? Amazon is the quintessential example here. They want to be in control of all these, what all these traders are doing. They're in control of their website, and they know exactly what is done on the website, and they will include and exclude and control as much as possible. This is the model of modern competitive behavior. It is about obtaining power in the form of control. Yeah. So that is the focus of today's lecture. And what we will do, first of all, is find ideas to express this control, the idea of controlling connectivity in undirected networks, or in other words, in the topology of the network. We know that trade networks, economic networks, are usually directed. They're trade flows, commodity flows, they're money flows. But the underlying structure tells us something about who has power and who has not. And that is the first part here that I will do today. So this lecture is totally about undirected networks. Yeah. So this is a kind of summary of what I talked about, right? So a critical property is the control of flows in a network. And how are we going to express that then? So it's a form of monopoly in some sense. It is a form of power, economic power. And in markets, it is about, I'm the only supplier. But here it becomes a little bit more subtle because we talk about a network. How do you have power in a network? There might be remote parts in a network that you have no grasp of, on at all. You're essentially only in control of the relationships in a network that are under your command, so to say. So how can we express that? Why is there still control in those networks? That is the main lesson for this week and next week, how we can express that. So connectivity is about paths. Are there paths connecting one part of the network to the other? That is, if there are strong connections, then it is called K connectivity. There are at least K independent paths between positions. And control was expressed in these ideas of cut sets and middlemen. And we talked about that last week. And we will build on that. We will take those cut sets and those middlemen, and we will link that with some economic ideas. So the first idea is what I call a threshold set, which is nothing but a cut set really but membership is expressed, right? So if A is a member of a cut set, then we call it a threshold set for position A. And so I take it away from the mathematics. I'm going a little bit to economics. It remains very mathematical, by the way. All of these concepts are defined mathematically, but I hope that the intuition will also come across. And so a threshold set is really that you have, that you in control of a bump, so to say, or you're in control of a tool that breaks the network, and that is exactly that cut set. Yeah. So all the sets of positions of which a position is a member that have this property of including a cut set, we call that the threshold environment of that position. So those are all the collaborations that this agent in that position can pursue to control flows in the network and control connectivity. That should be clear. Yeah. So this is about control. These are the basic tools to express control, threshold sets. Now, let's look at some properties immediately. Boom, you know. So when is something a threshold set for a position? If it includes a cut set. A might not be member of that cut set, but it needs to include a cut set in that T. Yeah. So also sources and sinks in the network have threshold sets because they can add themselves to a cut set, even though they will never be part of a real cut set themselves. Because if you remove a sink or a source in a network, it's an end node. That means nothing. I mean, there's no breakage. There are no components emerging by deleting those end nodes. Nevertheless, these positions have threshold sets as well, because you just can add them to these cut sets. Yeah. Now, in any connected incomplete network, so at least some links are missing, for all but maybe two positions. I say maybe two positions. That means either all positions or all but one or all but two positions have a non-empty threshold environment. So they are a member of threshold sets. And if we go to a connected network in which it's more widespread that links are missing, yeah, in the sense that the degree of a position is at most the number of positions minus 2, then all positions have a non-empty threshold environment. So they are members of these sets. Yeah. An important property is that if we enlarge threshold sets, they still are threshold sets. It is about containing these cut sets. Yeah. Are there any questions about these properties? They're very mathematically stated here. I hope the intuition behind them is clear. I show you an example to make it more clear. We see here a network of just 4 nodes, and only one link is missing, as you can see. The link between 1 and 4 is missing. The rest is all there. And this is an example of a network that satisfies the second property that we have here. Namely, it's an incomplete network. It is connected, but you will see that 2 positions will have an empty threshold set in this example. Yeah? Namely, what is the problem here? The problem is that there is only one real cut set here, and that is the combination of 2 and 3. If you take any other combinations, it does not really cut the network into pieces. The network is very small, first of all. So a cut set can be at most 2 nodes, but one with 2 and one with 3 doesn't do anything because 2 and 4 are connected. Yeah. 2 and 4 don't do anything either, and 1 and 4 together will not break anything either. So there is only one cut set. And as a consequence, all the threshold sets are with this cut set in there. And so one will never be member of a threshold set, because if you add one to the cut set, it is no longer doing something, right? There is no power here. Yeah. So just 4 is left if you add 1 to this cut set. It doesn't mean anything. It becomes meaningless. It becomes just, it doesn't, there is no power here, in other words, for 1. 2 and 3 have power because they are member of the cut set. And 4, again, is in the same position as 1. There's no power either. So thinking of power, how can you break a network? How can you disrupt this connectivity? Only 2 and 3 here have that power. Yeah, is that clear? Are there any questions? So the idea of a threshold set expresses this idea of basic fundamental power. Yeah, that is what we explore here. And we see here a clear example of 2 and 3 being in a position of power, and the other ones are not. All right, let's go to give a little bit more oomph to this, and let's describe then threshold sets that satisfy an additional property, namely threshold sets that are minimal in size. And what does that mean? If I delete from such a minimal threshold set 1 position, it is no longer a threshold set. In other words, it is no longer a cut set. So these are the minimal, it is a set of minimally required membership to have that power. If I delete any member of this partnership, it's no longer powerful. It does no longer disconnect the network. And so this is called a partnership. So a partnership is a special threshold set, namely everybody is essential. All the positions in the partnership are essential, and therefore A itself is also essential. Yeah. Any questions with regard to this definition? Yeah. Of course, we can then look again at all the partnerships of which a position is a member, and we call that then the partnership structure or the partnership environment of A. Yeah. Now, threshold sets was just the first step. Partnerships is much more relevant, as you can see here. These are much more meaningful because every member is really necessary to maintain that partnership. Yeah. So that is very important. Yeah. So let's go look at some properties. If you have threshold sets for a certain position, then for sure you have also partnerships. Yeah. Because if you have these entities, these threshold sets, you can take one and then throw away the unnecessary positions. You throw away positions until you hit this requirement that if you throw any other position away, it is no longer a threshold set. Yeah? So from any threshold sets, you can always go to a partnership. That is the idea. So if you have threshold sets, then definitely you have partnerships. Yeah? And if you have a partnership, then either the partnership is a minimal cut set of which the position A is a member. So those are cut sets that if you take away any position from that cut set, it is no longer a cut set. Yeah. Or it is adding position A to a minimal cut set. So partnerships are all about minimal cut sets. If we identify the minimal cut sets in the network, we identify all the partnerships. And membership of a minimal cut set gives you a lot of power. This is a position of power because you are essential for cutting connections in the network. Yeah? I hope that that is clear. Let's do another example. This is a bigger example, right? Here we have 7 nodes. As you can see, it's an incomplete network, but a connected network. It's undirected, of course. Now, if we look at this set 3, 4, 5, you see that this is a partnership for its members. Yeah, because it disconnects 1 and 2 from 6 and 7. Now, if you take out any of these nodes, 3, 4, or 5, it re-establishes the connection, as you can see. If we reinstate 3 in the network and only take out 4 and 5, you see that 1 and 2 there's a connection between 1 and 2 and 6 and 7 that goes through 3. Yeah, so that you see here. If you take out 4 from the partnership, 1, 4, and then to 6 and 7 establishes those connections. And 5, the same story. 1 and 2 can communicate through 5 to 6 and 7 as well. So we see here a clear partnership. Now, here's another one. You see there are quite a few here. If you pay some attention, you will see a lot. This is another one. It has exactly the same properties as 3, 4, 5, but now I've exchanged 6 for 3. Yeah, and so 1, 2, 3 are disconnected from 7 by this particular cut set, and this is a partnership. This is a minimal cut set. Yeah. Now, if you throw them together, the one that we had before and the 4, 5, 6 and 3, 4, 5 together, if you make one set from that, if we throw them together, we no longer have a partnership. We no longer, it's a cut set, but it's no longer a minimal cut set, right? So it is a threshold set for all these members, but it is not a partnership. And that is because 3 and 6, both of them are really not necessary here. They can be removed, one of them at least, and you retain the property of a cut set, so to say. Yeah. So this is the difference between a threshold set, a regular cut set, and a partnership or a minimal cut set. Yeah. I hope that that is clear. Are there any questions with regard to these concepts? All right. Okay, so this is idea number 1. And we are going to knit together these ideas. So this is cutting connectivity, and these are the basic elements of cutting connectivity, as you can see. Yeah. The second idea is thickness. Now, maybe you know this, in economics, we talk about thick and thin markets. And what are those ideas? Well, thick markets are competitive. We have many buyers and sellers in the market. In particular, many. Ideally, it is a thick market has a huge number of buyers and sellers. And a thin market is exactly the opposite. It's a market with very few traders, with very few buyers and sellers. And competition there is completely unrealistic, right? And that is why we have these models of oligopoly and monopoly for those situations. Can we extend these basic ideas of competition that come from economics to these trade networks, to this idea of network connectivity? Can we do that? Yeah. And indeed, we can do that, because what we then can do is count essentially members of these cut sets, members of these threshold sets. That is how we can determine thick and thin in some sense. And thick and thin is also this idea of K connectivity. If K is large and you have a substantial network, K connectivity with K large indicates a thick network. K connectivity with K small is a thin network in some sense. Yeah. So we already saw this idea a little bit, but here I will link this idea of thickness to threshold sets in particular. Yeah. So this is what I have here on the slide. This slide refers to this K connectivity as a possibility to think about this. But there is an issue with K connectivity because it's not really about counting the number of connections. It is really about how many positions are required to disconnect. So I can have many connections between certain nodes, but if they run all through the same set of positions, then I still have a non-competitive situation. I still have that a few positions or a few agents, economic agents in those positions can block me, can cut me off. And so K connectivity is not good enough. We need more specificity, so to say. We need to be more precise. And that brings back this idea of the threshold set and the partnership in particular. Yeah. So what I'm going to do is introduce some tools of counting, of measuring this thickness. And I use then these threshold sets or partnerships. Yeah. So this is the first idea, this thickness index. What is that? We will see that this idea is not really working very well. I will talk about that, but let's start with this very simplistic idea. I'm just counting the number of positions that are in my partnerships, right? So I take my partnership environment, this theta star. I look at all these partnerships that I'm a member of, and I'm just counting the number of members. And then I subtract myself from it. So this -1 is I take away myself. So how many other positions do I need to collaborate with in order to have power? That's really what is expressed here. So this tau of a certain position, this tau sub A, is with how many partners I need to collaborate in order to have power, to control connectivity in a network. Yeah. So every intermediary in a network is a member of at least one partnership. We talk about a non-trivial network. We talk about an incomplete network. We talk about one that has some relevance. There are not too many connections, but also not too little connections, so to say. It's a normal network. Then this thickness index might well be something to express this idea of thick versus thin networks. Now, if I take the minimum tau for all these intermediary positions, I can talk about the thickness of the network itself. Yeah? So it's the thickness of a position is how many partners that position has to collaborate with in order to control, in order to be able to break connectivity. And the thickness of the network is then the minimum thickness index over all intermediaries in a network. Yeah. Let's look at an example. This is quite a complex example, as you can see. There's somebody outside blowing leaves, so I hope it's not too disturbing. So here we see a network. You see there are a bunch of middlemen, and what you will see is that these middlemen have index 0, right? So thickness index 0 means I myself am a partnership. Now I discount myself. I don't have to collaborate with anybody at all in order to exercise control. Yeah, so that is the idea of this thickness index. If I'm a middleman, I don't need to collaborate with anybody, right? However, the other nodes, as you can see, they have thickness indices of 1. And what does that mean? They have to collaborate with at least one other agent in another position in order to form a partnership with control over the connectivity in certain parts of the network at least. Yeah. Now, there's an issue here. You can see immediately that even in this relatively non-trivial network, the thickness index is either 0 or 1. Why is that now, right? Why is it that, for example, this node here, this node that we have here, yeah, why the heck is that node not does not have a higher thickness index? Well, the reason is that this node can hook up with a middleman, maybe that node there that is included in the green box, to form a partnership. And so the problem of this thickness index, even though the basic idea seems to be very plausible and very natural, it's not very informative, because I do not differentiate nodes very well. We only differentiate one class from nodes from the other, the middleman from the rest, because the rest can just hook up with any of those middlemen to form a partnership, and suddenly the thickness index is just 1 higher than the thickness index of that particular middleman, which is 0. Yeah, is that clear? Any questions? And that is what we have here in this property. Take any intermediary in a network, look at the thickness of the network, and namely that minimum of all the thickness indices, then it holds that either the thickness of that node is tau, the thickness of the network, or it is 1 higher. Yeah. And so even in networks where you do not have these middlemen, but other configurations, you see that the same property. You get only 2 types of thickness indices, namely positions with the network thickness or 1 higher, and that's it. As a consequence, the thickness of the network might be of some interest, but the thickness of positions is not very informative. Yeah, so it is it's a kind of a bummer, this idea. It's simply not good enough. Yeah. Right. So I summarize some more properties here. Position A is a middleman if and only if it is in thickness index 0. The network has a middleman if and only if the thickness of the network is 0. And linking it with the idea of K connectivity, in a K connected network, we have that the thickness index is at least K minus 1. Yeah. Are there any questions about thickness? All right. Then on to the next idea then of measuring power. Can we really quantify power? That's the idea. Thickness was a rough measure, but it's not very exciting, not very interesting. Maybe the thickness of the whole network is of some interest, but it's not good enough. The next idea of quantification is much more complex and much more advanced. And the idea is based on a centrality measure from network theory called the beta measure, or the beta index, that I apply here to the idea of this partnership. And that is, how much is your membership of a partnership, how much is that worth? And if that worth, if we add all these values over all possible partnerships that you're members of, if we add them up, we get then the partnership index. Yeah? And that's essentially what we do. And it is in some sense the inverse of the thickness index. I will do 1 over the thickness in some sense. Yeah. So that is the idea of this partnership index. Okay, let's look at the definition. What do I sum up? Well, I sum up, first of all, overall partnerships that the position is a member of. So those are a group of positions that I am required to collaborate with in order to get power. Yeah, that's the idea. Now, how much power do I actually have in that partnership? Because all the other ones have also power in some sense. I do not get more power than anybody else in that partnership. So if we equally divide a power of 1 among all the members of this partnership, then I get 1 over the number of members of the partnership. Yeah. So my power in a partnership is 1 over that number. And then I just add up those over all partnerships that I'm a member of. And that gives me then my partnership index. And I give that the name rho. Now, is this a decent measure to measure power? Let's look at this example again that we looked at before. I took away all indications in the nodes. I just have my bare bones structure here of the network. Let's look at this. Let's look at it from the idea of cut sets. In particular, what are the minimal cut sets that we can identify here in this network? So those are the cut sets that break up the network into at least 2 pieces, such that if I throw away a position from the cut set, it is no longer a cut set. Yeah. So those are the minimal cut sets. Let's look at that. So again, partnerships are related to these minimal cut sets. Yeah. So partnerships are minimal cut sets, or they're minimal cut sets plus 1 additional position, namely the position that we are talking about. Yeah. So let's look at those minimal cut sets in this particular situation. So what are those? First of all, those are the middlemen. So these 3 we identified as middlemen, namely all of these guys, they disconnect 1 sink or source from the rest of the network. That's why they are middlemen. Yeah. And then we have 3 other minimal cut sets that are based on combining 3 nodes to really cut all possible positions from each other, slicing the network into 2, so to say. Yeah. And as you can see here, that is the row of those 3 positions in the middle, then the top 2 positions of those together with 1 of the side positions in the corner. Those are minimal cut sets as well. Is that clear? So those are all minimal cut sets in this particular network. There are no other minimal cut sets. as you can see. For example, this node in the upper left corner is an intermediary node, but has no power really. Yeah. Okay. Now, let's now make the partnership index work for us. Let's compute the partnership index for us. Yeah. So I repeat, all partnerships are minimal cut sets, or one position is added to a minimal cut set. So these minimal cut sets that we have identified, the 6 of them, those will drive the computation of the partnership index. And that's what we do. We identify that there are 3 middlemen from those minimal cut sets, yeah, that we identify. There are 2 core members of the other 3 minimal cut sets, and we call them beta. And there are 3 other members of those 3 other cut sets that we identified, and those are the loose members, so to say. Each of these gamma positions are member of 1 minimal cut set. And then there is this middleman in the corner there. We call him delta. So we identify 4 types of positions based on the minimal cut sets in this network. The alpha positions are middlemen. The beta positions are core cut set members of 3 larger cut sets, large minimal cut sets. And then you have the loose members of those 3 minimal cut sets. Those are the gamma positions. And finally, there's the delta position, who is an intermediary but not really member of any minimal cut set. And then there are the end positions, right? The sinks, sources, we can call them also end positions or leaves. They're also called leaves. Those guys, they're not really counted. They have no partnership index because it is completely irrelevant what they have. Yeah. Is this clear that we have these types of positions? Okay. Now let's explore their memberships of partnerships of these types of positions. Right? What can we say about the middleman, the alpha positions? First of all, the middleman itself is a partnership. It is a minimal cut set. So that is number 1. Number 2 is that if you add the middleman to any other middleman, you have again a partnership. So the 2 other middlemen, remember? So I can add the middleman that we talk about to either one of these other 2 middlemen to get the partnership. Yeah. And finally, there's a partnership with the 3 larger minimal cut sets. Yeah. What about the beta guys? The beta guys are all members of the minimal cut sets that we identified, namely the 3 that we identified. Yeah. And combining with any middleman will also form a partnership. Yeah. So there are 2 types of partnerships that they are member of. And gamma, the gamma guys, they are member of 1 minimal cut set. That's first of all. And secondly, they can combine with any middleman to form a partnership. So with any alpha. And finally, they can also form a partnership with the members of the other minimal cut sets, with the other 2 larger minimal cut sets. Yeah, you can add them to the other minimal cut sets. Yeah. Finally, delta. Delta can be combined with any middleman to form a partnership, and he can join any of the 3 larger minimal cut sets that we identified. Yeah. So alpha, partnership by itself, combining with any other middleman to form a partnership with the 3 larger minimal cut sets. Betas are members of the 3 minimal cut sets, the larger ones, and they can combine with any middleman to form a partnership. And the gammas, they are a member of exactly one larger minimal cut set. They can combine with any middleman, and they can combine with the other 2 minimal cut sets. Yeah. And finally, intermediary delta can combine with any of these minimal cut sets that we identified. Okay, so we can now compute the partnership indices, because for every type of position, we can now just add up these fractions. So for a middleman, what is that? He's forming a partnership by himself. That gives you a value 1 divided by 1, that is 1. He's a member of 3 larger partnerships, namely combining with the larger minimal cut sets. So it is a 3 times a quarter, namely 1 divided by the number of members of the partnership. There were 3 members in the minimal cut set. You add 1 to them, you get 4 members, so 1 over 4. Then there are 2 other middlemen that you can hook up with to form partnerships. And so that gives you 1 over 2. That is the membership of the partnership. And there are 2 of them, so we get 2 times 1 over 2. We all add it up, we get 2 3/4. So the alpha positions, the middleman in this network, they have a partnership index of 2 3/4. Now, what about the beta positions? Those are the core members of these larger minimal cut sets. Well, they are members of 3 of these minimal cut sets that have, these minimal cut sets have 3 members. So you get 1 over 3 for each of those 3. So it is 3 times 1 over 3. And then each of those beta nodes can join with the alpha node to form a partnership. Namely, the alpha node is a middleman, so you can hook up with the middleman to form a partnership. And that gives you then 3 times 1 over 2 members of the partnership. It's 3 times a half. If you all add it up, you get 2.5. The gamma positions, remember, they were member of exactly 1 minimal cut set. That has 3 members, so they get 1/3 from that. That is in the middle there of the computation, 1/3. Then they can hook up with each of those alpha nodes to form a partnership that is 1 over 2. You get 3 of them, so the 3 times 1/2. And then there are 2 other minimal cut sets that they can be added to, and that gives you 1/4. So you get 2 times 1/4. And if we add it all up, I get 2 1/3. And finally, the delta position. The delta guy can hook up with any of those 6 minimal cut sets. And when he hooks up with an alpha position, then he forms a partnership of 2 members. He gets a half from that. There are 3 of them, so it's 3 times a half. If he hooks up with the other minimal cut set, then there are 4 members to that. And so there are 3 times 1/4, yeah? So if you add that up, you get 2 1/4. And you see here that there's not much difference when you compute these partnership indices. It's all above 2, and there are minute, small fractional differences in the weights. This is a very uniform kind of network in which the power is relatively divided, as it should be clear from this analysis, that you have 6 basic cut sets, and you essentially compute for the network this basic power. Yeah. Are there any questions about this example, this computation? Yeah. So the partnership index is a more sophisticated measure of power, but it has its limitations as well. Let's be honest about measuring stuff. Whatever it is, there are limitations to how to express things and to quantify things. So what we do is put caveats with everything, and this includes also this thing here, the partnership index. It's not the end all of this. There might be much more interesting ways to measure this, but it is a way to measure power and to measure positional power in particular, related to the various positions in the network. Yeah. Middlemen are usually assigned high partnership indices, but it varies with the network. Sometimes it is not. So there is no clarity here. You cannot say the middlemen always get the highest partnership index. Yeah. And that is also a limitation. Yeah, it's a limitation. In the example, we had it. Yeah. Okay. Are there any questions with regard to the previous discussion about cut sets, about partnerships, the minimal cut sets, the measurements ways, the measurement of thickness, essentially, the measurement of this partnership index? All of this is, it's not the end of the story, so to say. It is something that it is incomplete, and it remains incomplete. It's not that interesting when you think of it. What we will do next is develop the idea of contestation, as I call that. That is much more interesting, and then you can directly apply to analyzing network economies. While these ideas of the partnership index, the ideas of the thickness, these are just ways of measuring things, but they are not necessarily popping up back in, from the theory when you do a model of trade and you try to compute prices and all that. It is not related to these indices. These indices stand by themselves, right? So if you have a higher partnership index, it is not the case that you can charge higher prices necessarily. It's not related to that. And so it's all rather limited in nature. It is, I just go over this to really give you an idea that you can analyze networks in this way, and you can think about competitive structures, and in particular about these flows in the networks and what interrupts these flows. Yeah? And we will be much more precise next with regard to this idea of contestation. That is much more valuable than just quantify this. Right? So I will not quantify contestation, but the idea of contestation is quite interesting and advanced, and I want to really emphasize that. Yeah. Okay. If there are no questions at this time, let's have a small break of a few minutes. Let's say we reconvene at 3 o'clock. And there are a few more slides in this presentation. It will not take more than 10 or 15 minutes, and then we're done. So, and then I will move to lecture 12 after that. Yeah. All right. Let's continue. There's one more thing to do in this lecture, and that is to introduce the basic notion of contestation, and that we will be developing then in the next lecture, essentially. Yeah. So contestation is really the equivalent of competition in a trade network. So it is an the real idea of competition. And In that regard, it is different from what we talked about so far. So far, we talked about cut sets, blocking connectivity or taking away connectivity, destroying connectivity. Contestation is the opposite. It is about creating connectivity. It is about making things happen, creating links, creating alternatives. Yeah. So contestation, the word contestation is used in market theory, in industrial organization, and it is about contesting monopolies in particular. So there's a whole theory in industrial organization that focuses on how a monopoly can be contested by creating an alternative to the monopoly, by competing with related commodities or related production technologies, but not the same. So the monopoly remains, but there is an invasion. You get monopolistic competition, so to say, that invades that monopoly, the space of the monopolist in particular, by creating new commodities, by creating something new, by being entrepreneurial. This is exactly the same idea. Namely, if I have a middleman, how can I diminish the power of the middleman? By creating an alternative. And the middleman should keep its power by blocking that creative innovation, by snuffing out any attempt to invade that middleman power, so to say. And that's exactly what we see. When we look at all these big corporations that we know, the information corporations in particular, Google, Apple, Amazon, all of them, one thing is in common. They are merging with very small entities at a frightening rate. So on average, Apple, for example, has multiple mergers or takeovers per week, and for years already. So every small innovative initiative that might threaten the position of Apple is immediately snuffed out. So it tries to counter this contestation, so to say. Yeah. And in market terms, it means new products, creating an alternative environment to create a new market, so to say, for people. But for in network terms, it comes to creating alternative pathways. And alternative pathways in the network are related to different commodities as well, because it is about trade. And what you trade in a network is related to what commodities. And so creating new pathways means usually creating new commodities, creating a new network, a new path. That means networking, creating partnerships, etc. Yeah. So this is your standard entrepreneurial activity that we already identified, and it is about creating business, in other words. Yeah. So contestation in networks really are referring to that here. Yeah. So a position can be contested in a network if there are other positions that can facilitate all the flows that go through that particular position that is contested. Yeah. So you circumvent, literally, you circumvent that position. You build alternative paths, chains around that position. And that's the basic idea. Yeah. So the thickness index roughly, very roughly, measures how contested the position is, but we saw already that the thickness index lacked quite a bit of information and power. It not really, might not really be that relevant. But what what it says is that if you have a high thickness index, there are a lot of alternative possible, right? And that is related to that K connectivity as well. If you have K connectivity and the K is high, there are a lot of pathways in the network. And so there are a lot of ways to circumvent positions. You can easily circumvent positions. And so a competitive network relates to a high K connectivity, a high K, and it relates to high thickness. And that's the only thing we can say at the moment, because individual thickness indices are not very informative. It is only the network thickness that is informative here, right? And that is what I refer to here in this slide. Contestation is in principle a dynamic concept, right? Also in market theory, when I talk about a contested market, it is something that might happen. There might be alternatives coming up, right? And these alternatives might undermine the position of the monopolist. This is exactly what happened with certain historical cases of monopolies, that monopolies faded away because alternatives became more important and alternatives were created. And so the advantage of the monopolist was undermined because they were literally outdated, right, by other activities, by new creations. Henry Ford built an empire based on the T Ford Model T car. It was based on a major innovation in production technology, the semi-automated production technology, brand new for that time. He was able to produce cars at a very low cost, and many of them, and he was able to sell many of them because he was able to price them so low. Now, this was undermined because other companies started to do the same thing, of course, and they introduced more modern models than the Model T. Henry Ford stuck to his Model T as if it was the gold standard and did not innovate that much. And for something like 21 years, he did not change that model at all. And meanwhile, his competitors created all kinds of more modern cars and more modern product, so to say. And so the T model literally was outdated and Ford lost market share as a consequence. So this is a historical example of this contestation at work, because Ford had a huge market share. It was a very close to being a monopoly. But it overstayed its welcome by just sticking to this old T model, and competitors stepped in. Now, how do you counter that? Well, merge, 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 take over, take over, take over. This is exactly what we see. Apple is a great example. If you go to Wikipedia, there's a special page with mergers for Apple, and you see how many mergers there were in the past years. Apple takes over literally all kinds of very small startups, and all because it wants to remain in charge. It wants to remain uncontested, as it is called. Okay, so this related to the dynamic issue of contestation, right? So it is the creation of alternative pathways that is an act that undermines a position's power. Yeah, and yeah. Ryan, you want to say something?
No, sorry, that must have just been a mistake.
Oh, okay.
Sorry about that.
Okay. So it is a dynamic process, very much, right? So I want to emphasize that. Yeah. However, we have a static theory. The network is a network, and how can we express that? Well, we can go from one network structure to another. Of course, we can do that, but in the same network, we can still think about contestation in the way of whether there are alternative pathways or not. And that's a positive concept. It is not a negative concept. It is not about cut sets. It is about looking at these alternative pathways. Let's do an example. Look at position 4 here, okay? Now, think about it. Position 4, can you circumvent position 4 in this network? Yes, you can. The functionality of position 4 is related to the connectivity between 1 and 7, really. Well, the connectivity between 1 and 7 can be facilitated by 3, 6, 8. So we can say that position 4 is contested by the group or the coalition or the club, whatever you want to call it, 3, 6, 8. And so 3, 6, and 8 combined have the same functionality as 4 because they can facilitate the connectivity between 1 and 7. Of course, it's more cumbersome because it involves 3 positions rather than 1, but nevertheless, 4 has it does not have huge power because it is limited by the fact that there is an alternative. And maybe 1 and 7 will never use that alternative, but because it exists, it is limiting the power of 4. That's the idea. 4 is contested, but still retains some power up to a certain level. But if it overdoes it, there's the alternative. There is 3, 6, 8. Now compare that then to position 7. Position 7 is a true middleman because 2 and 5 are disconnected from the rest of the network if you remove 7. The middleman has true power. It is different from 4 in that regard because 7 is uncontested and uncontestable even, unless real innovation, real entrepreneurship is brought to bear, and this network is fundamentally modified by creating new links, especially between 2 and or 5 and nodes 1, 3, 4, 6, and 8. Yeah, so you can only circumvent 7 by creating something new. Yeah, so that is very important, I would like to say. Yeah. Are there any questions about this fundamental idea of contestation? This brings me then to the conclusion of this lecture. Yeah. There are multiple ways to identify and talk about power. We did that. We talked about cut sets, partnerships. We talked about measuring thickness in the form of the thickness index. We saw it was not that informative for individual positions, but it was informative for the network as a whole. And we were talking about the idea of partnership index. Also, that has its limitations, but it's a little bit smarter than just a thickness index. It indeed forces you to really think about this whole competitive structure that is represented by the network. Yeah, so that is very important. And then finally, we had this fundamental idea of contestation, the fundamental idea of building alternatives, identifying alternatives, right? And to see whether you can circumvent positions or you can have alternative ways of connecting positions in the network. Now, we will take then that to the next level in the next lecture, lecture 12. This is all about contestation and defining that, and then we will see that there's a connection between contestation and these cut sets, there is a connection, and in some sense, this contestation is a positive way about to address this issue of blocking. Yeah? It is the opposite or dual of blocking in some sense. Yeah? Okay, so I have here a few points. So we brought together cut sets with threshold sets and partnerships. We talked about thickness, and we talked about partnerships indices. And then finally, I introduced the fundamental idea of contestation. Yeah. So next we go to directed networks. Until now, we only talked about undirected networks. Don't forget that. We will now go to the real deal. We go to directed networks, and we will repeat in some sense this exercise, but you cannot really talk about cut sets in an easy way in directed networks, but you can talk about contestation in a very easy way with regard to that. Yeah. All right. Are there any questions remaining with regard to this lecture? If not, then let's have a break. Let's say 25 minutes after 3, we start with the second lecture. I have to set it up and all that. So give me a few minutes to do that.